Well, welcome back. For those of you that attended the first lecture, I would like to start with a brief recap. Let me use this part of the board. On Monday, we had part 1, which was explaining why light. And one of the main arguments we gave was because we need more bandwidth. Part 2 was about modulation, how we embed this data into light to be transmitted. And part 3 was about some information about the hardware and the channel model. Now, an important point is that these two were for a particular type of link, which is the LED to a photodiode that we are going to call just PD. That was the type of communication. Now we are going to change. We're going to see that we can use the screens, we can use the sun, we can use cameras, we can use many different things to have visible light communication. So let's start. Now we are going to focus on communication between LEDs and cameras, okay, the ones that you have in your smartphone. And why? Because we have made the argument that we have billions of LEDs, but we also have billions of cameras, and hence it makes sense to connect them.
We don't see yours.
Oh, good. Thank you, Jack. I mean, it's just okay, good. So we have these billions of LEDs, now we have these billions of cameras, and we want to connect them. As we did on Monday, let me just do a quick questions here. Let's see. We started a little bit late, but let's see if we can try to make things fit. Open poll, full screen. So please just go to vbox.app or to that good QR code with that number, and I would like to know if you know what type of camera you have in your smartphone. So all of you have smartphones, all of you take pictures, videos, but I'm not sure if you know what type of camera you have in there. Okay, rolling shutter. Okay, that's the right answer. That's good. So we are going to talk about the rolling shutter effect and how it can be used for communication. Now, I have this question. Let's consider that we have an LED as a transmitter, just one light, like we did in the first lecture. And I'm going to give you two types of receivers, one photodiode and one camera. Which one of those two links do you think is going to be faster? The LED with a photodiode or the LED with a camera? I'm not sure if the question makes sense, right? So the LED is the transmitter, you don't change it. First you have a photodiode, then a camera. Which one is going to be faster? Okay, good. Actually, that's the right answer. So now we are going to go back into the presentation. The rolling shutter approach. First, let me tell you how you can use this. So the goal of these lectures is not only that you learn some new methods, but if you want, maybe you can start implementing them. And this was one demonstration done at a very good venue.
This is our demo submission for MobiCom 2014. This parallels our paper on indoor positioning using mobile phones and LED lights called Luxapose. Demo participants will all be given a mobile phone running our application. While the application is running, it continuously takes pictures. As you observe as it's taking pictures with a very short exposure, it is actually capable of capturing the fact that each of these LEDs is not stationary, rather each one is running a 50% duty cycle with a different frequency component. This allows us to label each of the LEDs and perform trilateration, such that when the user is near the testbed or walking through the testbed, arrows indicating the position, user's immediate position and orientation as they walk around the space show up in real time on the display. The user will be able to use both the front and...
Okay, so what you can see here is that they are using lights as these internal anchor points that is sending information, so you can obtain not only your position, but your relative direction. This application has two main components. How we send the IDs from the lights to the cameras, and then how we combine that information to get the actual location. Now, the actual location, the way that you do that, is used from robotics, and it's a well-known method that just uses some basic linear algebra, right? So matrices, vectors. Now, what I'm going to teach you is how we obtain those IDs, and that's going to be the rolling shutter effect that you're seeing on this side. Good. The difference between global shutter and rolling shutter is the following. If you have a global shutter camera and you have a fan moving, you will get this very clean image. But if you have a rolling shutter camera, which is what most of us have, we are going to get this distorted image. Hence, what does that mean? It means that you have an LED that is sending information that is being turned on and off, like we talked in the first lecture. If you have a global shutter, you will have just this type of image, but if you have a rolling shutter, you will have this sort of zebra pattern. Now, rolling shutter cameras are cheaper. That's the reason why they are in the smartphone. And global shutter cameras, they can be used for more advanced applications. Okay, good. So what is important to know if you're going to use the rolling shutter effect is that you know about the exposure time of your camera. So many of you maybe have seen these beautiful pictures in which you just have a scene at night, or you want to see how the stars move. And what you do is you put your camera and you have a very long exposure time. Usually your camera opens for a little time, integrates the amount of light that is there, but if you leave it open, clearly the building is not going to move, so that image remains static, but all the cars with the lights moving around will give you that effect. Okay, so that's the exposure time. You're going to control just how much you keep your camera on. Now, why is that important? Because if you want to use the rolling shutter effect for LED to camera communication, you need an exposure time that is very short, and I will explain that in a moment. Look what happens. Here we have different rows, so we take pictures, and that's a fan. That's how the camera is going to start taking pictures. Now let me pause this and let me try to explain it in some detail what is going on there. So this is me. These are my glasses, my body. The camera is not opening and taking a picture of all of me at the same time. What it's doing is, first, it is opening the first row. So it's taking only a picture of that. So I'm going to appear there. Now, then it's going to come for the second row. But if I would do a very fast movement, then this part would appear here. And if I would move back, then my mouse will appear here, and so on and so forth. So with the rolling shutter effect, the camera does not open all the pixels at the same time. It opens row by row, gets the information, and then it stores it. That's the basic idea, and that's why you have that effect. Now I'm going to tell you how that effect can be used to send IDs. So each light can send information. Good. So what do we do if we want to use this rolling shutter effect to get this effect of transmitting data? The most important point is that you minimize the exposure time. Now I will explain you why you get that zebra pattern. Let's say that you have an LED, a transmitter, and this is the on time, and this is the off time. The first row opens, and you will only see the LED on. So I'm integrating all that white light, and hence I'm going to have a row that is going to be white. This is going to be the row that we see, let's say, on top. It comes the second row. It still sees that it's during the time where the LED is on. And we continue like that. Look what happens by the time that we reach the fourth row. By that time, let's say around 80% of the exposure time is when the LED is on, but the remaining is when the LED is off. And that's the reason why this appears like a light gray. You continue doing this, and at one point there are going to be rows that are completely a position when the time is off. And hence, you obtain these dark points. That's the basic idea. So in that way, you can create these patterns. Now, you could say, what happens if I keep on increasing the modulation speed of the LED? And this is what happens in the second figure. Then you will no longer have that pattern. Why? Because it doesn't matter which row you are on, you're going to be having periods of light on and light off. They will be average, and everything will appear gray. And that's what you are seeing in these images. So here you have a very short exposure time, 161 microseconds. Look how crisp the image is. And now I'm going to increase that exposure time to get something similar to the images that we got before. This is beautiful for artistic views, but it's not good for visible light communication. And you see how it starts degrading. Okay, so steps number one, you download an app that can let you control your exposure time in your smartphone, and you try to put it to the minimum possible. That's the first thing that you do. After that, then you can start to control how many rows you want to have. Each one of these bands that you see, white, black, can have multiple rows. And you want to try to reduce that because you want to have multiple bits that can be embedded there. And then that's the next step. So what you're going to do is you're going to start increasing the speed of your light, but not so much, up to a point that you can have, let's say, a few rows that are very clear. And that's what we are doing here now. For example, here we have a carrier frequency of 1 kilohertz, and look what we obtain. We have a given number of symbols, I don't know, around 20. But if we increase that carrier frequency to 5 kilohertz, we have many more symbols that we can pack in. If you increase it too much, though, we are going to have all of it gray. So there's going to be a sweet spot in which you can embed the largest amount of information that at the same time is decodable. Okay, so those are the first step. Minimize your exposure time and try to find that sweet spot when you modulate your LED such that you can pack as much information as possible, so it's dense. Then after that, there's going to be the effect of distance. And this is one of the limitations of the rolling shutter effect. So what happens? This is the image that you have of a light at 50 centimeters, but if you're at 200 centimeters, at 2 meters, you can see that the image is smaller, and you will not be able to obtain the same amount of information. Correct? This is what happens. If you are sending data, let's say that this is your LED, here at the bottom, sending data. The information that you are sending at this point at the beginning is not being captured, it's lost. Then the camera starts moving at the rows that are capturing the information, and then after that, you do not read the packet again. So you can only read information during the periods where your area coincides with the timing of the camera. Hence, with the rolling shutter effect, it's not a means to transmit data. You do not transmit a file. You do not transmit text or images with that. It's just a method to transmit IDs. Every light will have one ID. 1, 2, 3, 4. Then you can send that information, which is small and can be contained in one frame, and then you can decode it. Okay, so that's the basic idea. There's going to be questions later just to see if you are understanding what I'm explaining. Okay, so we have step 1, minimize your exposure time. Step 2, see how fast you can modulate the LED. Step 3, just be mindful that you cannot send very long packets. You have to pack your information. And step 4, then you just use a little bit of geometry and physics to see how much information you can send. If somebody tells you, hey, I would like to develop this system, then you, as an engineer, as a researcher, would say, okay, you need to give me 2 pieces of information, how big your lights are, and what is going to be the distance that the user is going to have to that light. So that this is going to be the size of the light, S naught. This is going to be the distance, and internally you will have some parameters for your lenses and cameras. With that information, you will be able to tell your customer, yes, I can develop this localization system for you, or no, I cannot do it because some users will not be able to get that information, and hence, either you have to lower the ceiling so the image appears bigger, or you have to use bigger lights so we have more area that can be covered. So that's what you will need to do. Now, the modulation that we need to do with this. And this is something that we have learned in the first lecture. How many of you attended the first lecture? Okay, pretty much all of you. So then we do not need to go into this. And you would use Manchester encoding. So you could use Manchester, and that way you do not have flickering effects. But there's one more modulation that you can use, and that's frequency shift keying. So frequency shift keying, it just means, let me go back to this part, and that's what this paper does. Huh? You see these images here? The only thing that they are changing is the speed of modulating the LED. I'm just going to give one example. One LED, let's say it has periods of 500 milliseconds, the other one 250, 100, 30, maybe 10. So we are changing the number of bars that we have there. Then you can do some simple analysis to see what is the frequency that is being used by that LED, and that frequency determines the ID, the same as if you would have your internal GPS satellite. That's what FSK would do. The advantage of FSK is that it does not cause flickering effects, because as you can see, since we have the same numbers of ones and zeros and the width is the same, the average intensity is always the same. Good. So now you have the rolling shutter effect. You can send IDs, but that's not so exciting because you cannot send long pieces of data. Now I will teach you part 2, which is the full frame approach. And this perhaps would be also exciting if you're in computer science, in particular in ubiquitous computing, Internet of Things, or pervasive computing. First, let me show you the type of applications that you can have with the method that I'm going to teach now.
Augmented reality requires precise and instant overlay of digital information onto everyday scenes and objects.
So I'm not sure if you can see these. You're going to go and park your car. You have your phone. You're going to the little light, and the little light is telling you how much you need to pay per hour.
We present light anchors, a new way to display spatially anchored data in augmented reality. We take advantage of standard lights, such as LED.
Oops. Should not have done that because there's a few more.
Augmented reactor and process 240
Other
frames per
applications.
second. A 32-bit light anchor can be detected in roughly a quarter of a second. Light anchors can be used in different ways. First and most straightforward is to transmit fixed data. For example, the name of a building and its opening hours. It is also possible to encode a small dynamic payload. For example, this power strip reports its live power draw. This glue gun provides its current temperature and use status. And this fire alarm outputs its remaining battery life. Here we see a router that displays guest Wi-Fi credentials to visitors using its status lights, and a security camera that shares its privacy policy. This rideshare's headlights emit a unique ID to help passengers find the right vehicle. Finally, light anchors can transmit connection information, such as an IP address and one-time security token, which permits interactivity, as can be seen in this thermostat demo.
Okay, so now I guess by now I hopefully have convinced you that you can do a lot of nice applications if you know how to transmit information with light, and then you can use your smartphone to get that information. Now, once again, what was the key problem with the rolling shutter effect is that we cannot send long pieces of data because at one point we start losing them. The information needs to be very small. With this method, which is going to be the full frame approach, we will be able to overcome that, but because there's no free lunch, we will need to pay a price for that. And the price is actually an actual price. You will need a more expensive camera that has a faster rate, frames per second. So what happens? With the rolling shutter effect, we said that there's a sweet spot about how you modulate your light, and you can obtain these zebra patterns. What you do with this binary transmission, that I call the full frame approach, is you're going to slow down your LED. Okay, so look at this. It's not going to be that fast. You're going to slow down. You're going to slow it down so much that now you will have all the rows have to be on when the LED is transmitting, or off when it is transmitting. Okay, so that's the key difference. You're just going to make a slower LED. Now, if you make your LED too slow and your camera is slow, that's a problem because you're going to have flickering effects. Hence, if you want this to work, you need to get a faster camera. And by a faster camera, I mean something like around 240 frames per second for it to work. Okay, so that's the condition. What I'm going to show next was also a research paper that was doing Manchester encoding, something that you already know how to do. The camera rate was 240 frames per second, and the data rate was around 44 bits per second. But with that, you can do quite a lot of the applications that we already show in the first video. So now, the tricky part here is not to gather the data. Actually, you can do that if you want tonight. Instead of going to the sauna, you want to spend a couple of times just modulating your Arduino and recording that information, you could do it. Just get your Arduino, an LED, start recording that. You will see a series of figures, do some simple processing, and you will be able to get the signal that is on, off, on, off. The tricky part is going to be hand shaking. Okay, how can I detect that LED? In this case, there's an LED. This is the LED that is transmitting the information. And what you could do to identify that light is you could subtract 2 consecutive frames. You subtract them, and if the LED is on or off, you will find that difference, so you could identify the LED of that, or that's what you would think. That's not what is going to happen. Because you're going to be moving your hand a little bit, even differences, I will give you maybe a concrete example. Actually, this is a good example. So here, you have something that is black and something that is a little bit lighter. So if you move your camera, and at the beginning the row was on the lighter part, but you move it just a millimeter, then you're going to detect the black part. So when you subtract those two parts, you're going to have these sort of differences in intensity that may look like they are LEDs, but they are not. It's just that you're shaking your hand. So how do you overcome that? Well, the good news is there's already a lot of software for you that can do it. So some of that is going to be in this video. There's something called OpenCV. How many of you know of OpenCV? Oh, great. This, I mean it seriously. At TU Delft, I teach this course over 9 weeks. So how to transmit from LED to photodiode, from a screen to cameras, and LED to cameras. And we have some code, and there's OpenCV there. There's a lot of information in GitHub, so you could start also applying this. The basic idea is something called video stabilization. So there you see it shaky. Then you do some signal processing, and it's just having this beautiful view. Right, so then once again, this is shaky. And then you just apply what is called video stabilization, and then you just have this clean view. Once again, this is something for which you do not need to develop that code. That code will be available for you. With that video stabilization, then what we get is the following. Now, the basic idea is then that you, well, we will not go into the technical details, but now that you have that stable image that has overcome your video shaking, yes, a question? So the question was, what about focus fluctuation? So if the camera loses a little bit of the focus. That's a good question. I would say that if you do video stabilization, perhaps you will be able to overcome some of those effects, but you may need extra signal processing just to clean that up. I have not considered it, but that's a good point, because changes in illumination could also cause that same effect. Good question. Any other questions? No? Good. So then what you do is, hopefully now you have your delta of different frames, and you can identify that LED that is blinking. You see it turning on and off and on and off, and at the end you will be able to detect that LED. So that's a step one. And then after that, once you identify this LED, you can just create a time series in which you see when it is on, off, and you can decode information. You can decode the information from the building, the information from the Wi-Fi station, and all those examples that we saw at the beginning. Okay, so that would be the basic idea. How does this work? Well, depending on the quality of your camera, you can have here, they just did different evaluations. The range could be up to 6 meters, depending on where you are, if it's a dark environment or if it's outdoors. And the reception rate is relatively high, 80+%. But I would encourage you to go and try to attempt these methods. I cannot promise much after this, but I would say, I would put it this way. I really like students that then take an idea and continue working on it. So if you decide to do something like this, then feel free to send me a quick email later on, and then I can give you some more feedback if you get stuck somewhere. Or actually, please interact with Uber, and then we can see if you want to continue working on something like that. Okay, so now time to test a little bit of your knowledge. We have taught 2 methods using the LED with a camera, and we have the rolling shutter effect, and we have what we call the full frame effect, which was the second one. So the first question is, when we have this LED to screen approach, which one of these approaches allows to have more bits per frame for a single image? Okay, let's just go to, and let's see, if you pay attention, then if you do not answer well, then it means it's my fault. I did not explain it well. Let's see. Okay, so let's just see. So once again, is which one of these 2 methods allows more density of information, right? Okay, let's show the result. Okay, if you pay attention, this is random, basically. You know, we have been the same if I would not have given any lecture, and they just come here and ask you to give, this is almost like perfect random. It's very hard to get this. Well, this means maybe that I'm not such a good lecturer. Okay, so the one that allows you to have more bits. Okay, let me just ask the next question, and then we will see this one. Okay, so now, which one of these two methods, rolling shutter, does the zebra pattern, or the full frame, which is the one that we just taught later, allows you to transmit longer packets? Okay, let's see. Let's just wait a little bit more for those. Okay, there will be a few more there. Full frame, great. Okay, so this is good because it means that the answer here is correct. So I just need to go back and quickly explain you the answer for the first question, because I want you, all of you, to understand just the basics. So the first question was, which one allows to have more bits per frame? And let me just do this. So I think this slide will capture it. More bits per frame, so more bits per image, is going to be the rolling shutter effect, because each one of these bars represents 1 bit. So the density is going to be higher. The problem is, as we mentioned, that sometimes you cannot send longer packets, because if you're far away, you will not capture that. And the second answer that you gave was right. Longer packets is going to be with this binary transmission or full frame approach, because now you are not missing information. Okay, so that's the trade-off. Once again, the important thing that you need to think about this is, do you want me to do something like sensing or localization? Then you can go with the rolling shutter effect. Do you want me to transmit some small packets or pieces of data? Then go with this full frame or binary approach. Okay, that's the key message that you should have. Good. Now let's go to part 5. So we had part 1, part 2, part 3, part 4. So part 4 of this lecture was using the LED to the camera, not to the photodiode. So what is the same here is this. But what we have changed is the receiver. The receiver has changed. And we have taught 2 methods. Number 1 has been this rolling shutter. You could see it more to do things like sensing, localization. And the other one is this full frame or binary approach, where you can send small packets. Now we are going to go into part 5, which is a screen-to-camera communication. Now we are going to just, oh, sorry, good point. Please ask a question. Any questions up to this point, because we're going to switch gears.
How easy right now is to hack these devices, or is there any standard that I can look in a router in order that I can do that? Because in Arduino maybe it's easy, but if you want to go and do that in several devices, it could be a problem.
Good question. So the question is, how easy it would be if you want to develop this technology if there's already a standard? For traditional visible light communication, LED to photodiode, yes, there is. The IEEE, in the same way that we have a standard, for example, for Wi-Fi or Bluetooth, there's already a standard for visible light communication. For LED to camera, I am not so sure, but I know that they are commercial products, so there may be a standard, but I'm not certain about it. Any other questions?
Should we have a total control on 2 parts of the LED and camera to be able, for example, some person come to exhibition and everyone has some kind of phone, and can we use any camera, or we in our app we have to specify some parameters for it?
Yes, so good question is how easy it is to deploy the system like this if we have an heterogeneity of devices. So with the light, you will need to change it, clearly, to control it. And for your smartphones, you can develop an app. Now, within that app, in the same way, for example, if I give you an app that is going to check my steps, first I check if my accelerometer is there and if it's working well. You could develop an app that could try to check if there are ways to set those camera parameters, and then you could say, yes, your phone can decode this information, or maybe it will tell you that it has some limitations. That's something that could be done in Android when you start developing your app. Any other question?
For LEDs, Does color matter? What color are you using for the LED?
For the LED, what color?
Yeah.
It does. Sorry. Yes, so you can use color if you want. So something that we are not covering in this lecture is most of the LEDs, I didn't go that into the hardware, it's a combination of blue and yellow. I think, and that's how they get just the white that we have. Others, they have the RGB, red, green, blue, and then they combine that. And then you could also use those colors to transmit the information. So there are different techniques that can be done. The methods that I'm teaching now here is just for the basic LEDs, the cheapest LEDs, not the ones that have the RGB components. Good. Okay, so now what we are going to do is we are switching. So we are going to go and now change the transmitter from an LED to a screen. Now let's go quickly. Considering a camera as a receiver, so now we are not changing the receiver, what would provide a higher data rate, an LED or a screen? So you have now an LED or a screen that is transmitting information. Which one would send more data? Okay, let's just show the results. Screen. Good. LED was a second close, but yes, the screen is going to be a faster transmitter, and that's what we are going to focus on now. I forgot, until what time do I have? What time is lunch? 12:45, right? 12:30. Okay. 50 more minutes. Good. I think we are good on time. What is the idea? The idea is that you have QR codes in many different places. You go with your camera, you take a picture of that QR code, you get some information, and sometimes that's just a URL, a web page. But what you could do is, instead of just sending that single QR code, you could send a bunch of QR codes, and hence you do not get only the URL of the restaurant, but you could get the menu. So that's something that you could do. Then the screen becomes sort of a transmitter. What are some of the challenges that you are going to face if you want to do that? The screen is very good at sending very accurately a steady stream of information. So the frames that you see, 60 frames per second, 150 of your monitor, they are exact, they are very good. The problem with the camera is that you will have users with different heterogeneity, just what you were mentioning. Some may have 15 frames per second, others 240, and cameras are not very good. You will miss a lot of frames, right? So, for example, if you have that image that you're going, that video that you want to send there, that is a little bit annoying, because of the rolling shutter effect, you're going to have problems. For example, here we see a chessboard-like pattern, and look, we start with black here on this image, and on the other one we start with white. So at the beginning we start capturing the first image, then the rolling shutter effect happens, and we are going to start capturing the second image, because we are going from one frame. Let me just explain, I guess. Maybe it's going to be easier if we go quickly here. So what happens is that at the beginning you were capturing one image, and that image was in between the first frame and the second frame. So the first part of the camera captures one part, and the second part is capturing a different portion. And what this means is that when you're transmitting this video that I showed at the beginning, what you would expect to see is just this clean information, but you are going to have a lot of patterns that are being missed, some missed frames. It's just going to be a little bit of a mess. Hence, what is the important part of this? Let's say that you have information that you want to transmit, a poem. You put that poem into zeros and ones, then you put all those zeros and ones into different QR codes, and you're going to receive that, but sometimes you're going to miss part of that, and hence you're not going to be receiving your complete poem. So what do you do? Right? So you could be there and just wait until you get that information. So you could send, I will send you 10 packets, and then you miss packet number 2, so you wait for the next round, and hopefully you will get packet number 2, and then you are happy. But that's not a good way to transmit information. For example, here if we transmit 10 packets, what happens if we are so unlucky that on each round we just miss packet number 3 or QR code number 3? Then you need to stay for a 4th round. This is something that Shannon investigated some time ago. So the original information here would be only 33%, but the extra information that you need to send the overhead is 66%. That's not a good deal. You're using too much of your transmission just to send information again and again and again. So something that is done to overcome that is error correction codes. Don't worry, we will not go into the math. I just want you to understand the basic principle of it, because there's also code for it. You do not need to develop any code. This is something that you could do. What this system type of method does is the following. Let's say that you have 10 packets. Now what you're going to do is you're going to add 2 extra packets, 11 and 12. Now you need to get 10 out of those 12 packets. It doesn't matter which ones those are. And then you will be able to recover the entire information. And this is a method that is used widely. Okay, so then what you do in the example of the poem, you get your poem. Let's say that that poem fits in 10 QR codes. Now you are going to add some redundancy, something very small, a small redundancy. And then so long as you get 10 out of 12, you will decode your information. So it doesn't matter which ones those 2 are the ones that you're going to miss. This method is something that is used by Facebook, 8% of their warehouses, to protect your data. Do you think that, is there a question? Oh no, just stretching. Dropbox, Facebook, Google, you name it, what they do not do with your files is they just duplicate your files. They don't do that. They use these techniques to try to recover them. For example, if you have 2 files, A and B, and you just duplicate A and you duplicate B, if you lost the 2 of B, that's it. You lost that file. What they do is they do some mathematical techniques, and let's say these are the original files, A and B, and then you create some mathematical representations of those 2. So in this case, doesn't matter which 2 you lose, so long as you have the other 2, you will be able to recover that information. And this is something that has been used in the codes that you have for when you go to a grocery store, right? It's used there. In CDs, for those of you who are old enough to know what this is, and also they are embedded in QR codes. So what you would do if you want to apply this method? You get your data, you put it in a sequence of QR codes, then you can just go to something called Read Solomon codes. There are many libraries that are there. You're going to create these combinations. You're going to send your original frames, then you send the combination of frames, and now you have redundancy that will allow you to decode that data. Okay, so that's the key idea. I'm not going to go into too much detail here, but the basic concept, for those of you that are a little bit mathematically inclined, I know there are some physicists in this room. At the beginning, your information you see as an identity matrix, so this is the data that you have. Then the extra redundancy is going to be the one coming in the 2 rows. This is the information, let's say, that you want to send. And as you can see, the upper part of the matrix is exactly the same information that you want to send, and the other part is this error correcting information. If you are transmitting data and you miss 2 of those QR codes or 2 of those lines, then you can use just the encoding part to recover exactly the information that you want. That would be this last part here. Here you can see that the 2 original packets are there. The next 2 packets were lost, but we have the 2 encoding packets. And with the matrix, we have the first 2 rows of the original matrix, the encoded part, and we can recover our data. This was a little bit heavy. I promise the next part is going to be a little bit more exciting for you, but it's important that you learn about this. So, summary, the most important thing, because we're going to jump into the next part. Let me just put part 5. Has 2 components. You do a screen, SCR to camera, and you need to use these error correction codes. Read Solomon is a very popular one, error correction codes, to send enough redundancy to get all that information. What do you think is annoying of what we have been showing now? Because we're going to go into the next part. So what do you think is annoying? So if I would show you a video, and then I would just see QR codes changing like that, even if it's on a screen, they cannot go that fast. That may not be too good. It may cause a little bit of flickering effects. So what we would like to have is invisible QR codes. Okay? For those of you that attended the lecture on Monday, remember that I showed a video in which we took a screen, we put it behind a window panel, and then Sunlight was transmitting information, and we transmitted some data, but the data was invisible to you. You could see the video. That's what we are going to do now. Okay. So the key point is QR codes, we don't want to see them just changing, and actually we don't like them even to be present in our images. Look at this video, and then you will understand the concept between luminance flickering and chromatic flickering. There's a difference between just changing light on and off, so you get the average intensity, to changing colors. In this video, you will see that there's a QR code embedded, but it's invisible to the human eye. Okay, so then part one of this lecture was screen-to-camera communication. Let's just send a bunch of QR codes. Part two of this is going to be about how we make it invisible. And the way that you make it invisible, and it's captured here, is relatively simple. So as all of you know, a movie is just a series of images. Right? So you have a movie, let's say at 60 frames per second. And then what you are going to do is you're going to take one frame and duplicate it. So instead of being 60 frames per second, now you're going to transmit at 120 frames per second. So you duplicate this frame 1. This is F1, frame 1. This is frame 1, frame 1, exactly as it is. Then what you're going to do is you're going to have a QR code. And here you're going to have the negative of the QR code. Then you merge these two. When they come together, these are going sort of to cancel each other. And you will be able to see just the normal frame, but the QR code will be there for the camera to be seen. Okay, so that's the basic idea. In this video, you will see the same thing. This is just a normal video. Well, the video is not working. Oh yeah, there it is. You can embed this QR code, and here this is what the human eye will see, but the camera will see all that information being transmitted. And now what we are going to do is how you can embed that information. Oops, sorry. An important concept. Okay, an important concept is color spaces. Okay, so we humans see colors, and sometimes we see them in different ways, right? That's the reason why we have some people that you say, hey, that blue-green dress that was on the internet, right? What color do you see? We see them in different ways. Color spaces, in this case, are represented. This is the same image taken by the same camera, but if you see it, let's say, in your laptop that has more processing power, it's going to be seen different than in a low-power phone because the color space is different. These color spaces are represented in 2D, the ones that you observe here. And there's the green-red axis, so green-red, this would be this axis, and then you have the blue-yellow axis. And now you see these sort of ellipses, and we think that is going to be very hard for the human eye to distinguish changes. So these color spaces are going to be important for us because we are going to be modulating, let's say, color or lightness. The important thing here is that in this particular method, we are not going to change the color, we are going to change the lightness. And you're going to understand in a moment what we mean by that. So if we have a green, we're going to have a darker green, a lighter green, and we are going to start combining those two. For example, let's say now that 1 pixel in your video or image is the one in the middle. That's going to be L, the lightness of that color. Then what you are going to do is that lightness minus some delta, that's going to be for one of your QR codes, and then that lightness plus some delta L. And in that way, by combining the inner and the outer curves, you will be able to obtain the one in the middle. So the human eye will see just a normal color, but you will be embedding information. Some colors are easier to distinguish than others. Here you can see the contrast very clearly, but here you cannot see it as easy. And we are going to see in a moment how that affects the encoding of information. But it's not only color that matters, it's also texture. If I show you now the image on the other side, you will see that here you can notice the change in the light intensity. It's clear, but very likely none of you will be able to notice that change on this where the texture is more rough. So how do we use these two properties, the color and the texture? If I show you this image, the human eye, there are some colors that it's going to be easier for the human eye to see changes. For example, blue. We are very good sometimes at detecting that because at night we wanted to see, if there was a predator. Green perhaps is not so easy. And texture. So for instance, we see here there is a rugged surface, so here we can encode information. So what we need to do is we're going to see in this image which parts allow us to get the information more invisible. Once again, we have light, we have texture. How is that done? In the last lecture I said that I was not going to show any equations. Don't worry, this is super simple, but I just need to show you how this could be used. Because if you want to do this, by the way, you could also now, if you want to code a little bit, you can just get a video that you like. No, first take a picture that you like, just a picture. And then in that picture, duplicate it. Put your QR code. Go to, I don't know, a Python MATLAB that has a lot of libraries, embed your QR code, and just create a video. So you will see just a normal image, but you will be able to transmit information. How do you do that? The L star value that you see here is just the lightness of the pixel. So if you take an image, a pixel, into any processing tool, Python, MATLAB, whatever you want to use, it will decompose it into the hue, the colors, and the amount of lightness. Okay, so then you take the lightness, and that's the value here. You put it into this very simple equation, and look what happens. There are going to be two parameters, and in the paper that I referenced there, you're going to have those values. I think this is a value of 3 or something like that. So you put that value of lightness, you apply this relatively simple equation, and you're going to get the delta. So in other words, just so the idea is clear, what the tool is going to give you for every pixel in your image is going to give you the color and the lightness of each one of your pixels, and that equation is going to tell you how much of the delta you should use. So that's what you're going to be creating. After that, you get the delta that you should use, how much you should change that pixel color. And then you add, sorry about this, texture complexity. So this is the parameter that we obtained from the first lightness estimation. And then we see the complexity of the image, and we can make it stronger or smaller, depending on just how much texture we observe there. Once you have that, we follow the same process that we did before. You can just send QR codes, or you can have your own patterns. You add these Reed-Solomon codes, which is what we saw in part 5.1. And now you will be able to transmit information embedded in a movie or in an image. I will not go into these results. This was published by in a very good conference. There's the invisibility value. It's important that people cannot see the images, and there's also the data rates. And this is to answer your question. When you have a screen to a camera, now you see that we can go into the hundreds of kilobits per second instead of only 40 or 50 bits per second that we saw for the LED to the to the LED to the camera, and that's because a screen has so many pixels that it can have multiple channels transmitting in parallel. Okay, good. Questions? Yes.
Can I ask at this stage, lossless and lossy compression? JPEG versus PNG or GIF. Mm-hmm. All the data compression in also the movies, MPEG, they try to use this fact that human eye should not detect. But don't these somehow eliminate the information that you try to encode in there? So it has to be safe against distortions by these codecs, different compression codecs?
Good question. I have not thought about it. So the question is, when we have the normal signal processing toolchain of images or videos is we created, then we have this codec, then we have we use for sending information that we encode them to show it. And the question is how what we are doing of changing the lightness values could start changing all this information. That's a good question. I have not thought about it. Intuitively, I would say, no, we will not change, but it will add overhead because now we are adding more information that maybe will increase the complexity of the encoding. But that would be just a hypothesis that I would have for now. I do not have a very clear answer. That's a good question. Mm-hmm. Any other questions? Yes, there's one in the back. Let me just see.
The question here is kind of related to what Jaak mentioned here. When you talked about embedding or like hiding information in the video frames, do you target, I mean, the key frames particularly, or like the iframes, or it doesn't really matter?
I don't think it matters. The only thing that matters is that you have one frame that you can decompose, you duplicate that, and then you can embed your QR code there cleanly. So, but perhaps we can talk a little bit more. I didn't know about these exact questions that you have, and I would be curious to know more about it, because maybe that's more related even to video transmission or video compression.
Yeah, because one of them, it gets like more compression, I think. So I'm worried also about the data that is embedded. It will be distorted or like destroyed totally.
Actually, now based on these two questions, I think this is something important that I have not thought much about it. The impact that this will have in all the tool chains that we already have deployed in the standards, right, that process this information, and it would be important to look into that. Actually, you're both raising a good point. I have not thought much about it. Mm-hmm. And I'm not sure if the community has, because I have not seen that in the research papers that I have seen there. Yes?
Ask from Jaak.
From Jaak. So if I want to do the other direction, so if I basically want to kind of send information back to some kind of point of sales device or so with my phone and not just scan it from there, then I could potentially, because I don't see it, drop this embedding or the invisibility. So how much do I win or how much do I lose if I don't have to embed the QR code and make it invisible? So just really kind of have a rotating QR code with clear black and white things. Do I win something, or is this basically flawless, this method of having high frame rate and embedding it? Do I win frame rate? Can I then just communicate with 30 frames per second, or what is the advantage if I don't have to hide the QR code?
So your question is, let me try to rephrase it to see if I... Yeah, it seems that you want to have the flickering effect. If you don't care about the flickering effect, then you do not need to go through all this complexity. Because, let me put it this way, when you just transmit QR codes without trying to hide them, you just need some processing part, right? Either adding read Solomon codes to get information, and you can stop there. But if you want to hide that information, that's when you take into account the lightness and color. So it's not a compulsory step, but I would say that in most places you would like just an image that doesn't have a sort of a QR code that is flickering. That's the main advantage. That's the perception from the user.
But is it only complexity that we gain, or is it also...
No complexity. What we gain is that then the user does not need to be bothered by just a QR code. It's only that, and then you save that. For example, in the video that I show and in the lecture on Monday, there's this company that, let's say, has these transparent screens and maybe would show different videos, and they don't want to show QR codes. So then they just want to embed the information, and that's, for example, when these sort of techniques are valuable. Definitely. Good, so we have, let me see, 30 minutes, that's good. Until now, okay, let's just do this summary. So error correction codes, visible plus invisible QR codes. And now we are going to jump into part 6. Which is something where I'm doing quite a bit of my research, at least for the past years. It's called passive communication with light. And here I have, I think this is the last question that we are going to have with the poll. And the question is, what is the energy cost of digital communication? Now, a lot of things are expensive, but we just want to know if it's lower, similar, higher than the aviation industry. To give you context, you know that the aviation industry is pretty bad, right? I think it accounts for 1-2% of all the CO2 emissions, and it's not that a big part of the world flies. Only communication, digital communication. Yes, exactly, the transmission of information, just the transmission of information. No the deep learning, no the compute, no the... Okay, so we have, okay, let's show the results. Wow, almost a one-third for a moment. This is almost like a random guess. Okay, now we can stop because this is the last question that I have. Yes, so maybe let's go here. In 2012 or 2013, Times Magazine had a really nice article where they stated that we humans consume 50% more energy moving bits around the world than using all the airplanes around the world. 50% more energy. And that was 2012. This includes both wired and wireless. And why is that? If you think about it, wireless communication boils down to moving energy from one place to the other. I need to charge my phone. Energy is being transmitted, dissipated. So we are sending bits of energy. And that's a lot of information. And we are demanding a lot. Right? So this is something that was reported in Times Magazine. I think now wireless communication accounts for 1/3 of all digital communication. So it's a big chunk just for our demand, the big demand that we have. Between, I think, 1/4 and 1/3 is the latest things that I have read. So what's the problem? The problem is that now we have Wi-Fi, uses, I guess, 6-8 watts. Your LEDs, which are energy efficient compared to incandescent light bulbs, but they also use a lot of power, 10 watts, 8 watts. That's a lot if you're going to start transmitting information. And until now, we have been using these active devices, like your screen. If you take the backlight of your screen, behind your screen, there's a lot of LEDs, a big, strong light. So if you take that light out, and you just take your screen and put it behind a window, like in the first lecture, you save 80% of the energy that you're using on the screen and the laptop. And that's what uses the most. Huh? So what happens with active visible light communication? If you use an LED, it is valuable to communicate in terms of energy if you need that illumination to see. For example, in this case, we need these lights on because we do not have that much natural light. In that case, if you add visible light communication, you add an overhead, let's say, of 20%. Then it's good because you have to turn those lights on and you just add a little bit to get communication. But if we would have ambient light, it doesn't make sense to turn on these lights. And if you turn on these lights just for the purposes of communication, in terms of energy, is not good. We would be consuming more than what we are using with our Wi-Fi routers. So with this idea, we said, why don't we use sunlight, right? It's pervasive, it's much more powerful, but the key challenge is that we cannot modulate the sun. We cannot turn it on and off to have a broadcast channel. But how can we still exploit that immense amount of energy? And what I mean is not the following. I don't mean to put a solar panel, have a battery, and then turn an LED on and off, because when you do that conversion of energy from light to electricity, you lose like 60%, then you do from electricity back to light, you lose a big percentage. So I'm not saying that. How can we use that light directly from sunlight? And this is the idea. So there's going to be transmissive systems. And then you see this is a liquid crystal display, so you can see that it's changing between transparent and non-transparent. And this is exactly the technology that you have in your screens. So your screens, your pixels, just these little things that change between transparent and non-transparent. Hence, if we use this type of materials, what we could get if we have sunlight, we can just use a very small amount of power. By very small, I mean microwatts. And then we can control the level of transparency. We let sunlight go. We can block sunlight. And then we can let sunlight go again. And then we can transmit data. So what is the idea that I'm trying to tell is, if you have an LED, you need to give power to that LED. Oops, sorry. To transmit information. But you have sunlight. If you have sunlight, that energy is coming for free, so you just catch it in the middle and you save yourself all that amount of energy that you would use otherwise. So you just need to modulate the system. And if you think about it, this is what Alexander Graham Bell did with the photophone method that I taught in the first lecture. First I said, hey, let's use sunlight for communication, and I thought it was going to be such an innovative idea. And then I saw that Alexander Graham Bell did it in the 1880s. And I said, well, let's revisit the idea, but now that we have more advanced methods. What are things that we are trying to do? And I will show you some demos. This is not something that is being done by my group. Oh, sorry, Jack, you have a question?
Just on this Graham Bell visible light-based communication before radio. So it was purely analog signal, right? So that is a
big difference, yes.
Big difference. Yes.
Exactly, it was just analog. But you can imagine, sometimes I like to mix history with science. So you can imagine Alexander Graham Bell at that time, and just talking, singing, and then somebody hearing that on the other side. And it must have been an amazing feeling. Huh? I think he said that was his best discovery. Now with all the advances that we have, can we do something to use this sunlight? For example, one thing that we were thinking is if you are, let's say, here in Tartu, and you will have, this is the Netherlands, by the way, and you have these transparent glasses, you could start modulating them, and then you could just get sunlight to get information. So no radio communications, nothing like that. You just get your phone out, you have a photodiode there, you have a camera, and then you can get information. And if we think it that way, we can transform our windows into sort of wireless transmitters, sort of Wi-Fi, and then sunlight will come in one way, and then we can get communication on the other side. There are also airplanes, trains, so that's the vision. Can we transform our transparent surfaces in a way that then they can communicate information? So what we are doing? Something similar to Graham Bell, but digital communication. We had an emitter. This little box that you see there, something that we built. It looks big there, but it's just this big. Okay. The liquid crystal shutters are these. You see one dark here and one transparent. Light comes from the top. This is just plastic, by the way. What we can do is we can connect a keyboard, but we also have sensors. So you can type your name, a sentence, or we can have temperature, humidity information. And then what we do is we modulate this sunlight directly with something called ESSCaSS. So the frequency, let's say this frequency denotes a 0, this frequency denotes a 1. And on the other side, we have this box with an e-ink display, which uses very little power, a solar panel. And here, this was our first prototype. It says, I don't know if this is perfect, but it's getting there with a few typos. So the idea was that we could just deploy this system anywhere that we wanted, and we could use sunlight directly for communication. The data rate was low, 100 BPS, and then we were able to get 1 kbps. Now we are getting into around 60, 100 kbps, and I will tell you a little bit more in a moment. But that's the key idea. And the other thing is that you can not only use this method just for people. We are trying to see if it could be used, for example, for robots. In this case, this is just the area that we have outside TU Delft. Here you will see just a very simple robot. Sunlight is coming from the top, and there are going to be these some special optical materials that direct light on the side. And then the robots, I don't know why these two, it's strange. Okay, so you see these arrows. The robots will start to communicate with each other. So let's see what happens here. Let me just go forward. So these lights, these robots, they're not communicating with wireless. One robot is telling the other move forward, and they're just communicating via light. So sunlight is coming from the top, and they're directing it to the side, and they're coordinating their movements just to do something. Then you will see that they could try to push. Let's see, they're moving. This is now the next one is a collaboration task, in which you will see that one node cannot push the box we will try to move that box. Well, it's very slow robots, and this is even ×4, so you can see how slow these are. It cannot move it. Then it will try to ask help for the other robots. Say, come and help me, but they're just communicating via light, and then both of them will go and start moving the box. Once again, no RF communication, just with the ambient light. This is indoor ambient light, just the lights that are there in your ceiling. But we also run these experiments outdoors with sunlight. So in this case, now this is working with sunlight, and you can also achieve some level of communication there. Hence, this concept of just using sunlight not only to save energy, then it could be used not only for people, but with different devices. And this is something that is very close to my heart, because I have been devoting a lot of time to try to create the next system. Right now, we have these lights that are just giving us illumination. But I believe that lighting is the second highest source of energy consumption in buildings after heating and ventilation. And buildings are the highest source of energy consumption for people, right? So if you take a photo from outside the Earth, you will see a lot of lights. That's civilization, but that's also a lot of energy. There are some things called sunlight collectors. What they do is they have lenses. These are commercial products. So these are lenses that you can put outside, and then they have optical fibers. They guide sunlight internally. So for example, here, if we would have sunlight collectors on top, instead of turning on light, we would just have sunlight. And yes, we could open it. So, and then you could get your IR, UV, all these health benefits. What we are doing is we're trying to use this sunlight in two ways. In the lecture on Monday, I show how we are trying to use transparent screens. That would be what we have from here. But now we are trying to come up with a light, like visible light communication, but that works with sunlight. So what we are doing? We get the sunlight collector. The optical fiber is gathering sunlight. And in the middle, we are using something called digital micromirror devices. So it's a mirror that just oscillates very fast. And then you will have this light. Imagine that this light, instead of being artificial, it would be sunlight. So you can have your plant that is happy, you are happy, and then on top of that, you can get data. And that's what we are trying to achieve. Not only getting illumination, but data with sunlight. Where are we? This was our first prototype. So here you see the sunlight collector. At this moment, we are just kind of coupling that sunlight to our optical fiber. We are modulating it, and we are being transmitted. So this is, here you cannot see it, but there's a beam of sunlight. And then here we just have a photodiode where we transmit information. But I guess over the next months, we are working on a much nicer, better looking device. So hopefully that will be working okay. The data rate that we obtain now is around 50 kilobits per second. But before you laugh too much, 50 kilobits per second was also what we got in the 2000s when we started the internet. So what is the vision that we have here? As you know, when we have a wireless system, we have the physical layer, data link layer, that's connected to the IP addresses, and so on and so forth. We would like to see if we can come up with systems that instead of using radio, battery, or LEDs, they can just use natural light for communication to have sort of an eco-friendly way of having devices and people to talk. The data rates are low, are very low, but I think it's just an exciting topic to work on. And this is also something that we did about object and people sensing at my group at TU Delft. One of the works that we did was, if you are in a supermarket, you have a laser, you have your scan codes, and then you can get your products. But we said, can we, instead of using this laser, can we have sunlight? Instead of having these barcodes, can we just sense how people are sending our objects, and what information can we get about that? So what we did is, we did this with colleagues at Indea Networks in Spain. You could see here two cars, both of them white, both of them sort of sedan, while the other one hatchback. We just put a very basic photodiode that can work with this very small solar cell. And as the cars are moving around, we see these contours that are different. These are kind of the signatures of the car. And so then we can start detecting these cars with these techniques like dynamic time warping and things like that. We can also encode information on top to distort energy and send some data. And finally, this was some work done by a master student also at TU Delft. She did really well. There was a company called Tridonics that said, hey, you know, we have these lights, And when you're on the web, you can see when your customers are spending time on the web. And we cannot use the cameras of stores to see when people are spending time on given areas. But we have these lights with color sensors. So can we start doing something just to see if we can monitor people, but in a privacy-preserving manner? And this is something that we did. A color sensor is kind of a single pixel camera. So it takes all the colors that are there and combines it into a single one. So if a person is passing by in the same way that a car was passing by before, we can detect the contour. So first, the sensor will detect the color of my shoes, blue. Well, you can see that I like blue, blue, blue. It will mix blue and gray, the color of my skin, the color of my hair, just to start creating a unique signature. So this is something that we did in our building, our old building. We have one sensor, one color sensor here, another color sensor here. And now you will see how this works. So you will see first one person passing by, and the database will not recognize it, but it will detect its signature. And when it passes through the second one, it will say, oh, that's the same person. Another person will pass by with relatively similar colors, you will see in a moment. She is the author of this work. And then we will see, hey, a new person is coming. We don't have it in the database, but we can see later the same sort of pattern coming later, and then we can detect that that's the person. So now, with that, I will conclude my talk. Let me just to summarize here, we talk about part 6 is sunlight. And the key point that you need to do here is LCDs, liquid crystal displays. And part 7 was just a little bit more on sensing. And that is the idea of these 2 lectures, just so you have a better feeling about how light can be used, artificial and natural. Okay, thank you for your attention.
Thank you.